The only thing is how far can the whiteboard be seen. Find the right for the top. Thanks, thanks. Yeah, that would make it much more visible. So many of the things which I will outline, I am sure Professor Subir Sarkar would give much more details on that, because today's introduction he gave about the scales of the universe and general introduction to the universe. And by now, I hope you're familiar with the basic scales in astronomy. As you know, astronomy is the subject of studying stars, galaxies, using the same laws of physics that has been discovered in the laboratory. And one of the major miracles is that all the laws which you discover in the laboratory are applicable at scales of the order of billion gigaparsecs. Right, so by now you know that normal spiral galaxies, which if you view it from the edge on, the stars are distributed in the following manner with a central bulge and a disc-like structure. So the visible part of a spiral galaxy would look like the side view of a poached egg. Of course, if you see it from top, it would have beautiful spiral arms with a central bulge, and typically from the center to the edge of the stars, the distance is of the order of 15 kiloparsec, 20 kiloparsec, 30 kiloparsec. So let me also refresh your memory. 1 parsec is about 3.26 light years. I hope this is visible at the back. 1 parsec is 3.26 light years. Okay, I'll try to write it in bigger form. If you write it in CGS, it is 3 into 10 raised to power 18 centimeters. That is what is 1 parsec. 1 kiloparsec is obvious, it is 1000 parsec. And then 1 megaparsec is 10 raised to power 6 parsec. I'm saying very basic stuff because many of you might not have astronomy background to begin with. So typical spiral galaxies, their radius go from tens of kiloparsec to 30 kiloparsec, while clusters of galaxies, rich clusters like Abell clusters of galaxy, will have about 1000 galaxies, and the size of the cluster will go from few megaparsec to 10 megaparsecs. Now, as I said, the stars and the gases, namely those which are made of normal matter like protons, neutrons and electrons, these are visible. The evidence of their being there in galaxies, they go up to tens of kiloparsec. If you start measuring the velocities of stars in the spiral galaxy, in spiral galaxies, the stars which are part of the disk, they all have circular rotation about the center of the galaxy. All right? And if you plot the circular speeds, as a function of the radial distance. So if you are plotting the radial distance from the center versus the rotational velocity, what do you expect? When you are very close to the center of the galaxy, there's hardly any mass that can attract the stars and gases. Why? Because you all know from Newtonian physics the Gauss's law, which says that if you have a sphere of mass and if you are inside the sphere, the force is essentially due to standard Gauss's law. If you have a big sphere and you ask what is the gravitational force acting on a point here, the shell will not affect. It is only the interior mass that attracts, again because of Gauss's theorem. Okay, this can be proved, and therefore when you are very close to the center, the total amount of mass which pulls a star or any gas is only the mass enclosed within that region. And what equation the stars will have as far as the rotation velocity is concerned? The standard high school physics, the centripetal acceleration v square by r, where v is the rotational velocity. Let me write it in bigger form. So let me erase this part. I think the ink is too strong. Thanks. In order to keep any object in circular orbit, you need a centripetal force, and that centripetal force is provided by the gravity, so that v square rotation by r is given by gm by r, where m of r is the mass enclosed within that radial distance r. All right? So centripetal acceleration is simply the gravitational acceleration, where m of r is all the mass which is enclosed within a distance r. Because m of r is small, so what would you expect from this? Since v square rotational from this equation is simply square root of r square, sorry, gmr by r square. So therefore gmr by r is nothing but Kepler's law. So v rotational is square root of gmr by r, and hence mass being very small towards the distance close to the center, you would expect v rotational will be small, but as you go further and further away, the total mass keeps on increasing. So it increases, but lo and behold, beyond a particular distance it flattens. Now why is it a surprise? Why do you not expect a flattening of the rotation velocity? Because after some time there is no visible matter. The galaxy, disk galaxy, has a maximum radius r. After you go further away, the total mass enclosed within, as you see, is only within this mass. So therefore, after some time, we expect that the rotational velocity should go down, okay, as 1 over square root of r. Yeah.
So instead of plotting it rotational by r, if I plot it,
Yeah, I'm just plotting v rotational.
so right, if I choose my axis v rotational and 1 by r, that will give me a parabola, right?
Yeah, you can not v 1 over root r. So v square will go as 1 over r.
So that
So parabola will be 1 over v square versus r. So what you expect is that if all the matter was the baryonic matter, namely made out of protons, neutrons, electrons, then you see baryonic matter interact with light, and therefore the information you get out of light is matter has a maximum extent out of up to capital R. So very far to a great distance far away from this, you don't expect the gravity force to increase. Therefore, V rotational must fall, but what you see is they flatten out. And in 70s and 80s, Vera Rubin and her team, they charted out to great distance up to 50 kiloparsec, 60 kiloparsec. There, although you don't find stars, there are neutral hydrogen clouds, and I don't know how many of you know that since hydrogen has a proton in the nucleus, an electron cloud, the wave function around the nucleus, and proton and electron being spinning particle and charged particle, they have magnetic moments. The magnetic moment interaction causes the ground state. Again, these are high school physics, whose energy is minus 13.6 electron volt. There is splitting of the ground state because of the magnetic moment interaction, and the level is the split level has an energy gap such that if any transition takes place, the radiation is in the radio region with 21 centimeter. So by observing 21 centimeter radiation, you can find rotation speeds of neutral hydrogen cloud to distances up to 60 to 70 kiloparsec. But here I must tell you a little bit observational subtlety. What you observe is the red shift or the blue shift of the 21 centimeter line. So if the object is moving in some arbitrary direction, what you measure is the projected velocity along the line of sight. Okay? So therefore, while the circular velocity is always tangential, and the velocity you measure will be the rotational velocity only for the disk galaxy, which is being seen edge on. The moment the disk is inclined, you have to take the proper component. If the inclination of the normal of the disk galaxy to line of sight is I, you have to take sin I factor to find out what is the tangential velocity. So these are what observers pay great attention to find out what kind of rotational velocity you can infer from the data. Because what you measure is the Doppler blue shift or Doppler red shift of the stellar or neutral hydrogen gas cloud motion. And as I said, the data shows that V rotational, instead of going down as 1 over square root of R, it flattens. That immediately tells you that if standard Newtonian gravity and standard Newtonian laws of motion are correct, then flattening means that m of r by r at sufficiently large radial distances, they must be constant. In other words, the matter, so visible matter is not the only matter present, there must be some matter which don't interact with electromagnetic radiation, and as you go further away, your mass keeps on increasing such that m of r by r beyond a particular distance is a constant. All right. So this is, yeah.
So all these velocity points, are they just from hydrogen gas?
Also stellar motion. So what Vera Rubin did was, when we went to of the order of 40 kiloparsec to 60 kiloparsec, there are hardly any stars at such distances, but there are neutral hydrogen clouds. She measured that, but of course, a flat rotation curve again by her team was observed also by estimating the velocity of stars, which are, I'll give you some tutorial problem with exact data so that you can sort of dirty your hands and infer some actual observed result. So towards the end, I'll give you some tutorial problems. Right. So right now we concluded that if standard laws of physics, namely Newtonian dynamics and Newtonian gravity, they are correct, then there is no escape but to conclude that there is some kind of dark matter which is causing the velocity of rotation to flatten at large distances. Okay. Are there other evidences? The point is the evidence for such matter was even older than the rotation curves, and that was due to Zwicky, one of the maverick astrophysicists who has many predictions to his credit which was borne out. So maybe in the interim period when I'm erasing the whiteboard, you can ask questions. That's the best way I can gauge whether I'm talking trivial stuff or standard stuff. Right. First, I'll give you a tutorial problem. So please do it. So, tut problem number 1. Assume there are n point masses. Assume n point masses. And masses are mi, I going from 1 to up to n. Okay. Define the so-called moment of inertia, summation I going from 1 to n, mi ri square, where Ri is the radial distance from some origin. You have chosen an origin, and Ri are the radial distance from the origin of ith mass point. So construct this moment of inertia. Prove, and obviously, since gravity is universal, there will be always gravitational force between any two mass points. They are all neutral mass points, so there are no other forces but gravity. Prove that half second derivative of this moment of inertia is equal to twice total kinetic energy minus gravitational potential energy, total gravitational potential energy. So I'll read it out for those who are not able to see it clearly. Half second derivative of the moment of inertia is equal to twice total kinetic energy minus the gravitational potential energy for the whole system. So using standard Newton's laws of motion and Newton's gravity, derive this result. So this is the first tutorial problem. Okay. Now, many systems, particularly in astronomy, they have relaxed, meaning the shape of the system, you can infer from the time scale that the shape is not changing much over the age of the universe. As you know, the age of the universe has been measured up to 13 billion years. Maybe Professor Subir would differ with this value because your Hubble constant, your estimated Hubble constant is not as high as 70 kilometers per second megaparsec, right?
Pretty long anyway.
Yeah.
Let's call it 14 billion.
14 billion, yes. Okay. So the age of the universe is 14 billion years, and many of the systems which you see in astrophysics, particularly large systems, not stars, but large systems like galaxies, clusters of galaxies, the typical time scale, I'll talk about what decides this typical time scale after some time. They are of the order of billion years. And the so-called clusters of galaxies, which are the rich clusters have 1,000 galaxies gravitating, and they are almost relaxed, meaning the shape is not changing with time. Of course, they will be changing, but not on time scales less than the age of the universe. If that is so, then d2y by dt square will be roughly 0. So they are called virialized system. So this is really the virial theorem, and for many gravitating systems in astrophysics, you can assume that there is hardly any change in the moment of inertia. So for our purpose, we will assume that since systems are virialized, average kinetic energy is equal to half of average potential energy. So for astrophysics, very often one uses so for astrophysical systems, our virial theorem would read twice average kinetic energy is equal to minus average potential energy. It is obvious that you better have a minus in front of the potential energy, because gravitational potential energy is negative, while kinetic energy is always positive. Okay? So this will be our virial theorem. But the exact virial theorem is the tutorial problem I have given. Please do it. It's a very straightforward problem. And this form of virial theorem is very, very useful in astrophysics. It gives us a lot of important things. Particularly, Zwicky used it for Coma cluster. Coma cluster is a rich cluster of galaxies, about 1,000 galaxies randomly moving in the self-gravitational potential. And what he found, I'll give you a detailed problem concerning that, but let's do some order of magnitude calculation. Okay, so 1,000 galaxies, n is about 1,000, 10 raised to the power 3. Assume that the galaxy mass, roughly each galaxy has a mass by estimating the luminosity. You can find out by assuming for the standard stars mass to light ratio, you can estimate the mass. of a galaxy, and typically it's 10 raised to the 11 solar mass. Again, for those who are unfamiliar with the numbers, one solar mass, that is sun's mass, is 2 into 10 raised to the 33 grams. Okay. So 2 into 10 raised to the 33 grams is one solar mass. Now, typical dispersion velocity. So, if sigma square is the, take sigma square, where sigma is the velocity of a galaxy, and average it over. So, square root of that for a typical cluster is of the order of 1000 kilometers per second. Okay, and size of a typical cluster, let's call it the R cluster size, is, let's say, 1 megaparsec. Now apply the virial theorem to this and check whether a typical cluster, if it is relaxed, if it is bound, then it must satisfy the virial theorem, and check the numbers. Okay. So can someone do a quick calculation of what is the total average kinetic energy, what is the total gravitational potential energy, and so on?
This mass is for what, sir? I can't read the subscript.
So m gal. So roughly
Of
one galaxy has a mass of the order of 10 to the 11 solar mass, and I said one solar mass is 2 into 10 to the power 33 grams, and remember, 1 parsec, 3 into 10 to the power 18 centimeter, 1 megaparsec is 10 to the power 6 parsec, and so on.
So we use the sigma square thing as the V square RMS.
Yes.
We can use it to compute the kinetic energy.
Total kinetic energy. Yes.
Huh?
Total kinetic energy.
Yeah, total kinetic energy using N and M.
Correct.
The potential energy would be calculate the self energy of a sphere of a certain radius.
Yeah, total mass is known. So gm square by R cluster. So minus gm square by R cluster is a measure of the gravitational potential energy. Total m is, you have to include the factor of n.
Yeah, Nm.
Or there's another way of doing it. You can take one galaxy and find out its kinetic energy, then find out the gravitational potential energy of one galaxy due to all, and compare. So please do it. I'll only give you the result. The result is that you will find that twice kinetic energy, average kinetic energy, is much greater than minus average potential energy. If you take m to be due to the visible matter alone. So what is the physical conclusion you can draw? That if the mass estimated from the stars of these galaxies were the only mass, then you can't have these clusters of galaxy to be bound and virialized. Bound meaning what? When is a system bound? If there is attractive potential whose potential energy goes to 0 at infinity, any such bound system, what should be the energy? Negative. Negative, right?
But if 2t is greater than minus t, then it's not negative.
Yes.
And total energy is positive.
Because, yeah, total energy, average energy is also average kinetic energy plus average potential energy. So if you can show that if virial theorem and this implies that the average energy must be negative. So please do the calculation. These are important. Please do the calculation. These are simple calculation. And convince yourself that total energy turns out to be positive. If total energy is positive, why is it a problem?
That means it's not a bound object.
But that's only a word, meaning they can go further away, they can escape to infinity. If the total energy is positive, they can all just go to infinity. But the fact that you are seeing clusters of galaxies all bound, okay, about 1 megaparsec in extent, there's a problem. So this is what Zwicky immediately realized way back in 1930s. He did this work when Chandrasekhar was doing his work on white dwarfs. So way back in 1930s, by studying Coma cluster, he immediately concluded that there is dark matter. Of course, he called it hidden mass or hidden matter. Anyway, those are all words. Words don't have much significance. What is more important is the operational meaning of terms in physics, that which can be measured. Right. So therefore, what this implies is that if standard physics is valid even at such large scales, then there has to be dark matter. Okay. In fact, you can show that you need total amount of dark matter is almost 100 times more than the visible matter. Only if you have net mass to be 100 times more than the mass you infer from stars and gases, that kind of dark matter you require. For rotation curves for galaxies, it is about 10 onwards, but for clusters you need 100 times more dark matter than the visible matter. Okay. Are there any questions? Yeah.
Sir, is it safe to assume that gravitational galactic clusters, they are not stars inside them, galaxy inside them, they are not moving away from each other due to Hubble parameter, but the galaxy clusters as a whole are moving away from each other?
Yeah. So, okay. So, yeah, there's an important point. So far, I had not talked about scales at which the Hubble redshift applies. We all know that the universe is expanding, and as you go to larger and larger distance, the rate at which the distance between any two galaxies is increasing is very large, of the order of from 60 to 70 kilometers per second per megaparsec. Now the question is, at what scale should you apply the Hubble expansion, and at what scale you don't bother about Hubble expansion at all? Remember, the Hubble expansion occurs, you see Hubble expansion on scales on which universe is homogeneous and isotropic. But the real universe, of course, is not, the full universe is not homogeneous and isotropic. I mean, in this room, things are not homogeneous and isotropic. The fact that between you and me there is a space, there is air and so on, means that the density is clumpy. But when you go to about 1000 megaparsec, that means 1 billion parsec or 1 billion light years, and assume all the matter you have over this scale is smoothened, then imagine a box of size about 1 billion parsec, and count the number of galaxies in this imaginary box and translate this box around. Then you'll find that within Poissonian error, the number of galaxies in this 1 gigaparsec cube imaginary box, that number of galaxies within Poissonian error is fixed. That tells us that over long distance scale, universe is homogeneous and isotropic. And then on such scales, Hubble flow is very important. Theoretically also, the so-called Friedmann-Robertson-Walker model, which follows from general relativity. If you take Einstein's general relativity, assume that the density is homogeneous and isotropic, and solve the instance equation, you either get a expanding universe or you get a contracting universe. In fact, before Hubble discovered observationally, Lemaitre, one of the Belgian general relativists, he had already suggested that there should be, our universe is expanding. Anyway, that's a long story, I don't want to go into that. Now, so therefore on such scales, Hubble flow is very important, but we are talking about gravitational bound systems which are clumpy, and the scale is of the order of million parsec. On these scales, the Hubble flow is not important. So these galaxies are bound to each other, and we need not bother about the expansion of the cluster due to the Hubble flow.
Sir,
Yeah.
from where you are getting this 1 billion length scale?
From observation. So I mean, in science, measurement and observations are the thing. They are the arbiter for whatever models you.
Which are greater than clusters and superclusters?
Oh yeah, clusters are, as you can see, but superclusters are of course galaxies and clusters which are sort of in the form of shells, filaments. They can be of the length of a filament or a shell can be 1 billion light year. Yeah.
So when you just mention about just let's say certain scale there is a clumpy structure, but like beyond that scale we can see a repeatedly.
No repetitive, there is no periodicity. We are talking about statistics. So unlike solids, a crystal, where there is a perfect repetitive, you don't have such things. The real macroscopic world is very dirty. You don't have such order in the real macroscopic world. Even crystals are very special systems. Not all substances which we see are having that crystalline order. There are amorphous substances, completely. What is your question?
So that what I was confused. Is it like if I just study one unit, let's say, I can put the analogy of result for the other?
No, you can't do that. You can't do that. But what you can do is this. You can say that if I am talking about scales more than billion light years, then you can apply Friedmann-Robertson-Walker model to study various aspects. You can't apply Friedmann-Robertson-Walker model at 1 megaparsec. It is not valid because the density is not uniform at such scales. So that's the reason why very often people, first time they hear about Hubble flow, they ask, are we also expanding? With the universe expanding, so therefore is this duster also getting stretched? The answer is no, because Friedmann-Robertson-Walker geometry doesn't apply on such small scales. At this small scale, the general relativistic solution, which is more applicable, is a Schwarzschild solution, where there is no expanding or stretching of matter. Right. So therefore, I hope by now you are convinced that if standard laboratory physics is correct, then one of the simplest solution is that there is dark matter, meaning there must be objects which don't interact with light, because the only way we infer their existence is from gravity. Gravity, of course, is universal, so anything that is there must have gravity, because Newton and Einstein told us that anything that has energy and momentum associated with it would have gravitation associated. So that is universal. Okay. Right. So now let me give you how much time do I have? I very often lose track of time. About 10 to 15 minutes. So it's high time that I give you the problems. One problem I have already given you, namely the Virial theorem. Show first, or rather this is a second, but doesn't matter. Show that if you take a galaxy like a spiral galaxy or an elliptical galaxy, then take the, for spiral galaxy you can take the rotational velocity. For elliptical galaxies where there is not much of regular rotation but objects are moving randomly, show that v to the power 4 at distances r from the center is proportional to the luminosity of stars which are located within a distance r from the nucleus. This is called the Tully-Fisher relation. Okay, so fourth power of the relevant velocity, rotation velocity for spiral galaxies, while dispersion velocity for stars in the elliptical galaxy. L of r is radiation from stars, all the stars which are located within a distance r from the center. So this is called the Tully-Fisher relation. I'll tell you what you have to assume while deriving this rule. This is observed result, by the way. Tully and Fisher deduced this law by looking at many spiral galaxies, and very often this result is used to find out the distances of clusters of galaxies. So the assumption, basic assumption you have to make is that the surface brightness, namely the radiation, the intensity of radiation from the surface of a galaxy. What you see when an astronomer sees a galaxy, he sees it projected on the two-dimensional sky, and the surface brightness, which is amount of energy coming in per unit area of that disk, okay, per unit time, that is roughly constant over the entire galaxy. So surface brightness is constant. That's an assumption you have to make. And the mass to light ratio is a constant. It doesn't change over the entire galaxy. The amount of mass to light ratio doesn't change within the galaxy. Okay? So there's one problem. And then for Coma cluster itself, I'll give you a problem. So this is the Coma cluster. I'll give you some data first. So again, the total number of galaxy, you can take it to be 1000. Sigma square, average sigma square, you can take it to be 5 into 10 raised to power 11 meters square per second square. Size R cluster, (1.9) into 10 raised to power 22 meters. Okay. And you can assume that the average luminosity of a galaxy average luminosity is about 8.5 into 10 raised to power 7 times solar luminosity. I'll also give you the value of solar luminosity. So average luminosity per galaxy is 8.5 into 10 raised to power 7 solar luminosity, and solar luminosity is 4 times 10 raised to power 33 erg per second. Sun typically emits 4 into 10 to the power 33 erg per second. That is what is called the solar luminosity. Okay. So for this problem, find the total average energy of the cluster, find average energy of the cluster, and also find out twice T plus V for the cluster. So twice average kinetic energy plus average potential energy, and find what is the total, and estimate. So there is no space, but estimate the amount of dark matter in order it is a virialized system. So since there is no space, please note it down. The final question is estimate the total amount of dark matter. All right. Finally, so already I have given you 3 problems. Okay, maybe tomorrow I'll give you more problems. Right. So far, what we figured out is that if Newtonian gravity is all there to it, then what you have is that there is evidence for dark matter. The question is, what is the form of dark matter which we have? First of all, the dark matter should be such that they should be bound by gravity. Okay? They cannot be like photons. You can't, unless you create a black hole, you can't trap the photons. Okay? So if they are zero rest mass particles, then you will not be able to have them trapped in a cluster or a galaxy. So they must have non-zero rest mass. So they can't be massless particles. Okay? So the question is, what kind of particles can constitute dark matter. And this is the field where Professor Subir Sarkar has made important contribution about various kinds of dark matter. Initially, when I was a graduate student, and probably when Professor Subir Sarkar was a graduate student, neutrinos were considered to be, Professor Kaushik, he was your supervisor, right? And Kaushik's one of the celebrated work, McClellan and Kaushik, they gave bounds on neutrino masses based on cosmological expansion. So those days, we used to think that maybe neutrinos would be the right dark matter. But then over the years, solar neutrino problem, atmospheric neutrino problem, the oscillation, they have given us some idea about the masses, and the masses are too insignificant for neutrinos, the standard neutrino, electron neutrino, muon neutrino, or tau lepton neutrino, to be considered as serious candidates for dark matter. So therefore, over the course of this GYAN series of lectures, I am sure Professor Subir Sarkar will highlight on many other candidates. But one of the things which seems to be very clear from the Large Hadronic Collider experiments is that candidates which are called WIMPs, or weakly interacting massive particle, which were some time back very popular candidates, and particularly supersymmetry in particle physics, if supersymmetry is a right way of unifying the various forces, there is a supersymmetric extension of electroweak theory which can give you massive neutrinos and many other nice properties. If supersymmetry exists, then they predict a full sector of particles, every particle which is a sort of counterpart of the standard particle. If you have a quark, then there will be squarks supersymmetric, which will be a boson, while if you have a photon, which is a boson, there will be a fermionic counterpart photino, etc. And there was a belief that these heavy supersymmetric particles would be candidates as far as WIMPs are concerned, but now LHC and many other experiments have given very stringent bounds which seem to suggest that even if such particles are there, they cannot explain dark matter, the evidence for dark matter. And tomorrow I'll give you another problem. There's another aspect to this problem, namely modifying the Newtonian dynamics, the so-called modified Newtonian dynamics MOND, which was championed by the astronomer Milgrom, which says that there is no dark matter, but you have to modify when the accelerations is too small. By the way, one problem is when you do the rotation curve, rotation velocity, find out what is the acceleration. What is the acceleration? V square by r. Find out what is the value of this acceleration. So MOND is inspired by the fact that the acceleration at such large distances where you have flattened rotation curve, these accelerations are very tiny. And Milgrom suggests that the laws of Newtonian dynamics holds good only when the acceleration is above a particular critical value. For small acceleration, your Newtonian dynamics have to be modified. But there are problems associated with MOND idea, particularly there are evidence of clusters and clusters of galaxies interacting, the so-called bullet cluster, where you do see that baryonic matter, because they undergo viscous dragging, they have electromagnetic interaction. Therefore, baryonic masses, they have undergone viscous damping, so they are concentrated in the central region when two clusters of galaxies have passed, while the dark matter still are moving because of their inertia. And so therefore, MOND will have to do many things to explain such astronomical events. But anyway, I'll give you tomorrow a problem. It's always good to also look at it from a different perspective. So therefore, I'll stop here, but you can ask questions. So feel free to ask any question, whatever you have.
So since we know that MR is proportional to R for the region where dark matter is supposed to be,
Yes.
we can infer from that the density distribution of dark matter.
Yeah, there'll be a problem. I'll give actually the distribution. There is also Frank and some other. I'll give you proper. There'll be numerical problems. So R greater than a particular value, these density distribution is such that M is roughly proportional to R beyond a particular.
And so for the third problem, won't we need the mass of each galaxy as well?
Sorry.
For the third problem, won't we need the mass of each galaxy?
You can use the mass to light ratio for a typical galaxy like spiral galaxy, where we know that take our galaxy for example. So our galaxy has the total luminosity, you can take it to be about 10 raised to power 10 solar luminosity, and mass be about 10 raised to power 11 stars, so multiply by the mass of the sun.
So is there a relation between shape of a galaxy or a type of a galaxy and the total dark matter mass it has?
Not that I know of. Maybe Professor Subhi Sarkar can. The question is there a correlation between amount of dark matter and the shape of the galaxy? Of course, elliptical galaxies are much bigger, and the total amount of dark matter is also very large. But is there a correlation between the morphology of a galaxy and dark matter?
Not clear. The mass to light ratio, including the dark matter, is of order 10 for most of these galaxies. As to whether there is a specific correlation of the galaxy type, is not something that you would expect in the standard so-called hierarchical galaxy, the model that is normally assumed for the
Formation of
the galaxies. In detail, whether there is or not, it is true that dwarf galaxies, the smallest ones, are far more dark matter dominated. Their mass to light ratios become greater than 100, which means they're 99% dark matter. So, in some sense, the smaller the scale, the more dark matter, but as Milgram pointed out and he mentioned, it's a scale in the acceleration, not in the spatial extension. So, the test particle acceleration is also smaller. That is to say, it's less than this magic value, which is the Mond value in the dwarf galaxies. I'll discuss this in one of the lectures. Current record holder is mass to light ratio of almost 1,000. That's like 99.99% dark matter in small galaxies.
I mean, as you can see, that these really are challenging the existing paradigm in astronomy and cosmology. This is a very exciting field now. Yeah.
So these ratios that you told about dwarf galaxies, the mass to light ratio which you
Yeah.
quoted, is that for satellite galaxies?
Yeah, this is a particular satellite of our Milky Way.
Because
So on the basis you can see it.
for satellite galaxies, because for the total system, the bigger galaxy, which is satellite we are talking about,
Yeah.
the most of the mass is located, the light mass is located in the center of the larger galaxy.
This is the Milky Way. This is our galaxy, of which this is the satellite.
Yeah. So when we move away from a galaxy, we assume that since velocity for hydrogen gas is not decreasing as
Yes.
it should,
Yeah.
so away from the center, the most of the mass which is present there should be due to dark matter.
Yes.
So and these
So this is a dwarf galaxy moving in that halo
in
of
that
dark matter.
in that belt
Yeah.
only.
The halo itself has a mass to light ratio of order 10 or so. But this object in it is even more dominated by dark matter. That's what we infer.
Sir, is there any conversion factor between dark matter and dark energy as we have equality of the square for ordinary matter?
Well, one can show that if your dark matter particles have mass less than 10 to the power minus 23 electron volt, then under certain conditions such ultralight dark matter particles can also masquerade as dark energy. Because what you need for dark energy is that the pressure should go as you know, rho, rho minus p, where rho is the energy density, while energy density goes as rho plus p. So you can show that if you have ultralight dark matter particles, they can also masquerade as dark energy. And there's also Chaplygin gas, which can, these are all theoretical ideas. We still don't know what the dark energy is really. So Chaplygin gas can also serve both as dark matter as well as dark energy. Yeah.
Winds are not the foremost candidates anymore.
Can you speak slightly louder? I can.
Weakly interacting gaseous particles are not the foremost candidate any longer. Then which particles or theories are? Is it axions?
Well, I have a vested interest. I'll go for ultralight dark matter particles because of some work I have done with one student on forming supermassive black holes with ultralight dark. There's another challenging problem. I don't know whether Professor Subir Sarkar will talk about it. There's another big problem that many of the distant quasars, they show very massive black holes, billion solar mass and more. And these quasars are very distant. I mean, the light we are receiving were emitted when the universe was billion light years. Recently, there's a galaxy, there's a quasar which has been seen when light from it is coming when the universe was 690 million years old. And it has a billion solar mass black hole. How do you form such big black holes when the universe was so young? So this is another puzzle. And one of the things which I am looking at it is that whether you can use some kind of Bose-Einstein condensation for this ultralight bosonic dark matter particles and create supermassive black holes. So you can have ultralight dark. Witten and Tremen, following our work, they wrote up something saying they use the word fuzzy dark matter, because normal cold dark matter has some problem. I don't know whether I'll have time to discuss. Maybe Professor Subir Sarkar, that central region, they predict more satellite galaxies and which are not seen. So this problem is very exciting now. I mean, we are really at the moment sitting on almost at the verge of a great breakthrough coming in. Yeah.
How do you get that bound of 10 to minus 23 electron volt?
Yeah. So, I mean, normally, if you have a scalar field, as you know, the scalar field, if you have a very light scalar field, then its energy density will be half phi dot square plus V phi. Well, the pressure you can show is half phi dot square minus V phi. And if you have a very light scalar field, then V phi, if there is no other potential, is m square phi square. So a light scalar field, its potential m square phi square can, the energy density being half phi dot square plus m square phi square, pressure being half phi dot square minus m square phi square, you can create for such light scalar field, it can be dark matter as well as dark energy.
It depends on the balance between the kinetic term and the potential.
Yeah. Yeah.
Any more questions?
Yeah, there's some.
There are some ideas like strongly interacting massive particles and all of that.
Yeah, yeah. So there are
They are very light.
at short range, very short range, they can interact.
Also light in mass.
And
Light, I mean, mass is very small, as I understand.
there are bounds, but as you know, the gravitational wave arrival time and all that, the bounds on photon mass is very, very small. So photons cannot be candidates for dark matter.
No, my actual question is that, as I understand that dark matter helps in the galaxy formation and all of that.
Yes, yes, of course.
So, can such a particle like strongly
I think he's
strongly
talking about
interact with
strongly
that particle.
interacting dark matter, lecture 6, please wait.
Yeah.
Till the day after tomorrow.
Okay.
And do these particles actually interact electrically?
Yeah, they better not interact with light, otherwise you could have just seen them. The fact that light doesn't give any information, I mean, there's no light being emitted from r greater than 50 kiloparsec from a galaxy. So therefore, that's why it's called dark, that they don't seem to be interacting with light. And all charged particles interact with photons, so they can't be charged. Yeah. No. That's a good question. So dark matter is there. So one simple thing is, if your dark matter density, I'll give you a better, the so-called Frank something density profile, but rho going as 1 over r square. If dark matter density goes as 1 over r square, you can show that at large distances, the total mass will go proportional to r. So in other words, the dark matter density increases as you go towards the galaxy, but the point is the total mass inward enclosed within r is still dominated by baryons, even though density of dark matter shoots up, but the total dark matter mass very close to the center of a galaxy is negligible compared to the baryon. You can ask why. The baryons, they have other interaction, so they, star formation, viscous rubbing. The baryons, when the galaxies were forming, by losing energy, they keep on settling towards the center. While dark matter, the only major interaction is gravitational interaction. So they cannot lose energy and settle down to the central region. So they form a bigger halo.
I'm getting jealous, Patrick. They're asking you all the questions which I'm going to answer in the next 9 lectures.
No, but the answers will be more detailed.
I'm jealous only because they didn't ask me any questions.
Oh, that's always the case of Blackboard. That's why I prefer
Yes,
Blackboard.
I think you're right.
They are warming up to asking your lecture. Okay, so I think we should close for now for lunch, and we'll be back at 2:30. All the participants can go to the HRDC canteen and eat there. You will have to pay, unfortunately, for your food. So local participants can pay only for lunch, and all the non-local participants should pay for the entire week during your first week or whatever. Okay. Also pay for